Good morning.
Good morning.
Okay, so today, just a quick review of how the PDA is built, and then a couple of examples, and we can talk through a couple more without doing the details, and that's it. So then Friday will be office hours. So I don't know that this will take the full 50 minutes or not. We'll find out as we go through. As a reminder, I put up the homework for this week. There's only one homework for this module, and it's due next Monday. It's already available to you. And there it is. Let's see here. As a reminder also, discussions are available for each of these things. And if you have questions, that's a good place to put the questions. If you have any questions about grading or about the content of the course, contact me through Canvas, please, not through email. Okay, so these things are just like finite state machines, but they have a stack. And because they have a stack, remember, we have to do some additional actions to take that into account. And the actions that we have to do is add a stack alphabet, because the alphabet for the stack doesn't have to be the same as the alphabet for the input symbols. In addition, in the stack alphabet, you're going to want something to mark the bottom of the stack, or an empty stack. So I'm using $sign for that. There's nothing magical about that. And you also have to designate what the empty stack symbol is inside that stack alphabet. So our 5 tuple for finite state machines turns into a 7 tuple for push-down automata. And the first 5 are 5 of those 7 you're already familiar with. So Q is the set of states, sigma is the alphabet by which the language is composed, Q naught is the initial start state, F is the set of final states, delta is the transition function. We'll have to modify that to accommodate the stack. And then the 2 additional items are gamma, which is the stack alphabet, and Z, which is the empty stack symbol. To process this, we go from a function that takes 2 inputs, current state and symbol, to a function that takes 3 inputs, current state, symbol, and what's on top of the stack. And the function, instead of producing 1 output, which was the next state, produces 2 outputs, the next state and what string do you push onto the stack. We also may find situations where we allow these things called ADA transitions. I don't have any examples of that in the 2 examples that I provided here. ADA transitions, so we have a notion where we can process nothing and yet still do something to the stack. The reason we have to do that is sometimes you need to pop more than 1 thing off the stack, and technically you can only pop 1 thing at a time. So what an ADA transition does is, if you have to pop multiple things off the stack, you can do that using the ADA transition. And or if you remind me, I'll give you an example of that at the end of class. Our acceptance criteria also changes. We can accept through accepting states. In other words, if you end up in a final state, then you accept the string. Or we can accept based on empty stack. Don't create machines that do either or both, one or the other. I'm going to do empty stack. And again, this is the formalized way of saying that. If you start process string U, starting with the empty stack, starting in the start state, and you end up in some state, we don't care where, but you have the empty stack symbol on the stack, then you accept. You're not allowed to just slap an empty stack symbol on top of a stack that is not empty and claim that you have an empty stack. So that's the acceptance criteria. So one of the outcomes, if you go back and read those, is that you can express or explain what the acceptance criteria for these models of computation are. And that's what we're talking about. Remember, this is a language recognizer still. We're just recognizing languages that have certain characteristics. The machine should accept all strings in the language and reject all strings outside of the language. Another way to say that is the string or the machine will accept all and only strings that are in the language. Okay. Talked about the transition function. The graphics look a little bit different. All the states look the same, but now we have to include on the graphics portion the idea that we're not just processing a symbol from the input string, but we're also processing the top of the stack. And we do that actually by popping or removing that top of stack element. And then we also have to not only designate what the transition is using the arrow, but designate what string we're going to push onto the stack. And remember, if you push a string onto a stack, it shows up on the stack inverted, because remember, stacks are last in, first out. So if you push a 0, 1 onto the stack, then the top of stack is actually 1, because that's the last thing you put in there. So we're going to look at the symbol that we're processing from the input string and the symbol that we got from the top of the stack. That's what causes this transition. The actual state transition is shown by the arrow, just like before. And then we add in, oh yeah, but we're also going to push this string on the stack. You are allowed to push lambda onto the stack. You are allowed to push nothing on the stack. That's how you basically remove elements from the stack. Questions so far? Okay. As a further note on the graphical forms, because you can have a very large number of arrows, go back to this one. I've got an alphabet that's just AB, that's only 2 elements. I've got a stack alphabet of 0, 1 gamma, that's 3 elements. Now I have 6 possible combinations. So I have 6 possible arrows. Every single state would have to have 6 possible arrows. Many of them would lead to a place where we know we're going to reject the string. So as a convention, I'm just not going to show those. And the assumption is anything that is not shown is leading to an immediate rejection of the string. Technically, if you were to draw it out, it wouldn't be immediate. You'd go to some place, it's kind of like a garbage state where you never get to accept the string. A garbage state in this case, because we're doing acceptance by empty stack, is you push something on the stack and the state that you're in never ever takes it off. So you could never get an empty stack. So instead of showing all those, which would be a lot of visual clutter, if a transition is not shown, immediate reject. Okay, so now let's talk about this canonical example, A to the n, B to the n. That's the canonical non-regular language, and the reason is because you have to keep track of how many A's you have seen before you start counting B's. And if you think about it, forget the machine, just think about it in a generic, how would I do this common sense folksy way. You say, well, every time I see an A, I put a symbol on the stack. Every time I see a B, I take a symbol off the stack. And if I have an empty stack by the time I'm done, the numbers of A's and B's must be equal to each other. Then you draw the machine. Now, because in this particular case, the A's and B's can't be mixed up. All the A's come first and then the B's. So in this particular case, every time I see an A, I put a symbol on the stack. Then every time I see a B, I remove a symbol from the stack. And once I'm processing those B's, if I ever see an A again, I should reject, because that violates the rule that all the A's came before all the B's. So this thing looks like this. and it's just got two states. I start in state 0, and I start with empty stack. So the first thing that I process, first of all, if I have a string of 0 length, is that allowed in the language? You have to always consider that. In this case, it is. If I don't process any string, I have a $sign on the stack, so I have empty stack, so I'm okay. I accept the empty string. Otherwise, I'm going to have some A's followed by some B's, and the very first time I see an A, I'm going to have an empty stack symbol on the stack. So that's what this transition here is about, a $sign. And we said every time we see an A, we're going to push a symbol on the stack. I'm going to use the zeros to count. I notice in this example, even though my stack alphabet is 0, $1 I never need to use the ones. So the very first thing I should see is an A with a $sign on the stack. That's this transition. I'm going to stay in Q0, but I'm going to push the $sign back on the stack and then add a 0, because we said every time we see an A, we add a symbol, and I'm using the zeros. After that, I'm going to start to see A's with a 0 on the stack, and I'm going to put that 0 back on the stack and add another one. So every time I see an A, all I'm doing is adding a 0 to the stack. Once I start seeing B's, I need to remove a 0 from the stack. And so B0 that's, by the way, the only legal option I can have, right? If I see B $sign, I should reject that. If I ever see a 1 in the stack, something's gone horribly wrong, because I'm telling myself I'm not using it, right? So the only possible thing here is I've seen some A's, now I'll see a B. Since I've seen some A's, there will be a 0 on top of stack. So B0 transitions me to Q1. And what's going to happen in Q1 is that's just a reminder that I'm not allowed to see any A's anymore. I'm only allowed to see B's. So what have I done? I saw a B and I removed a 0 from the stack, and that's what we said we wanted to do. Every time we see an A, we add a 0 to the stack. Every time we see a B, we remove a 0 from the stack. So since that 0 has already been removed, I'm not going to put anything back. I'm going to put lambda back on there. In other words, put nothing back on the stack. Once I'm in Q1, I just keep doing that. B0 lambda, because I'm going to keep, every time I see a B, I'm going to pop a 0 from the stack. I'm not going to put it back. If I have more A's than B's, I will run out of string, and by the time I'm done processing, I'll still have a 0 on top of the stack, therefore I should not accept. If I have more B's than A's, at some point I'm going to be in Q1 seeing a B from the string and the $sign from the top of stack, and I'll know that I should reject that also. Questions so far about how I'm drawing this? Okay, so drawing this part is a little tougher, I think, than the finite state machine, because you do have to consider all the different options that can come up with the stack alphabet. Once you've drawn this, though, and you convince yourself that your logic is sound, transliterating to this 7-tuple form is straightforward. Q, sigma, Q naught, and F are just like before. Now F here, I've got the empty state, empty set. Remember, I still have to use set notation for F. So F is the empty set, meaning I don't have any accepting states, and that's because I chose to accept by empty stack. I knew I was going to use the $sign for my empty stack symbol, and then I still have to write out the transition function, still do it in tabular form, but now it's a little more complicated, because for the single input alphabet symbol A, I have to consider 3 separate possible top of stack values, the $sign, the 0, and the 1. And the same thing with the B, the $sign, the 0, and the 1. And I have to consider 2 actions. One is the state transitions, and one is what did I push onto the stack. So I wrote this in an Excel spreadsheet. It just seemed easier. You can do it by hand. You can do it in MS Word tables, whatever you like. But the way to read this is again, you go from the graphic. A dollar sign. What state do I go to? The arrow says if I'm in state 0, I go to state 0. If I'm in state 1, I should never see that, therefore I'll reject that. So in state 0, a dollar sign, I stay in state 0. And for A0, that's here, I stay in state 0, so I do that. And then over here, I talk about what's pushed on the stack. Okay, if I saw a dollar sign, I need to push $0. And if I saw a 0, I need to push 0, 0. It should match the picture exactly. And notice most of these squares are not filled in, which kind of gives you an indication of how many arrows I didn't draw, right? Every one of those shaded squares would have been an arrow on that diagram that would not add any informational content to the diagram, but would add a lot of visual clutter. That's why I'm allowing us all not to have to put them all on there. It's still deterministic because we specified an action for if you see them, which is reject. On the stack, I'm pushing, if I get B0, I'm not pushing anything on the stack, so that's what's happening here. B0, nothing on the stack. If I ever see a B dollar sign, something's gone wrong because I've had more, now I have more B's than A's, so I should reject, and I'll have nothing on this, nothing added to the stack. And I'm not using the 1 in this case, but it is in the alphabet, so I have to specify what to do with it. So A1, B1, no matter what, reject. Pausing for questions. Okay. Here's an example of processing the string, and I put the image of the machine down there as a reminder. So if I wanted to process this string AAABBB, I start in state 0. Again, I did this with an Excel spreadsheet. I start in state 0. My top of stack is $, or empty stack, and I still have to process the whole string, AAABBB. So what's the first thing I process? I process that input symbol A. I pop the $sign from the stack. And according to the picture, what new state do I go to? I go to 0. According to the picture, what did I push onto the stack? $0. So now what does the stack look like? It's $0. Because remember, last in, first out. Now, I'm still in state 0, but now my stack looks like $0. I've processed the first string A, so I still have AABBB. I processed the first symbol, which is an A. I pop the 0 from the stack. According to the picture, I stay in state 0. According to the picture, I put 0, 0 back on the stack. Now I have 0, 0 $sign. And if you're looking at how that stack looks, you know, look over here. I'm in state 0 and I have 0, 0 $sign. Well, that should make sense. I've processed 2 A's, and every time I see an A, I'm going to push a 0 on the stack. I've processed 2 A's, and I have 2 zeros on the stack. I processed the last A, and I push 0, 0. Now I've processed all 3 A's, and I have 3 zeros on the stack. I just have B, B, B left. This is the first time I get a state transition. So I process the first symbol, a B. I pop the top of stack, which is 0. And according to the picture, I go to state 1, and I don't put anything back on the stack. So since the stack was 0, 0, 0 $sign, and I popped that first 0, the new stack is 0, 0 $sign. And then that just keeps going until we're done. By the time I'm done with the string, I've got nothing left in my string, and my stack is $sign, so I accept. Pausing for questions.
So some of the arrows that aren't there, they would still have to pop stuff off the stack, I'm assuming.
Yes, so let's do, oh wait, let me see if I can do
Because I'm just wondering, because eventually they'll keep popping stuff off the stack and they'll reach the $sign. And if we always accept the dollar sign,
Right.
wouldn't that mean we're accepting
And,
strings not in the language?
yeah, and I have an example on the next example for that. Right. So let's say I did 3 A's and only 1 B. After 3 A's and only 1 B, I'd be here with this $00 sign. I can't highlight this because it's an image. All right, so let's see. If I wanted to process AAAB, that's fine, AAB, right? The very first time I process the A, let's see, let me put the stack over here. So the stack starts out like that. And once I process the first A, I have AB, and the stack looks like that. And then I process the next A, and the stack looks like that. And then I process the B, so I have nothing over here. And my stack looks like that. Whoops, that. So what I did is, I stopped processing and I have a 0 on top of stack, so I would fail that. That would be a reject. Now let's do the other way. If I start with just AB, after I process the first A, I'm going to have $0 sign on the stack like before. And then after I process the first B, I'm going to pop that 0 so I have dollar sign. And then right away I should reject, because look what I'm doing. I'm popping B dollar sign, and on my picture I don't have a transition for that. B dollar sign is not shown on the picture, it's shown as reject. And in terms of my transition function, I said B dollar sign, whoops, over here, state transitions. B dollar sign is reject. B dollar sign, it's not applicable to talk about what you're going to put on the stack because you're rejecting. Did that answer the question?
So we're not accepting the string every time we see the dollar sign, we're just ending the string at that point.
So it depends on your language, but you're right. Every time you see, just because you saw the dollar sign doesn't mean that you'll accept the string. The reason that we know that's true is because the time you process a symbol, since you always start with empty stack, you're going to see the dollar sign as your first top of stack element for every single language, right? Like right here, right? When I was in Q0, I said, the first thing I'm going to see is an A with a dollar sign because it's empty stack. So that doesn't mean that I stop processing. It just means that I keep going and do whatever I need to do with the stack. It's once you're done with the string, well, two things going on. Once you're done with the string, you check to see if the dollar sign is top of stack. If it isn't, it's reject. Or you may find situations in your language that says, man, if I ever see this dollar sign again, something's gone wrong. And the thing that went wrong here is I have more B's than A's, right? How can I fail the A to the N, B to the N language? I can either have more A's than B's or more B's than A's. And if I have more A's than B's, how will I know it? I'll process the whole string and I'll still have a 0 on top of stack. How will I know if I have more B's than A's? Oh, I'll process the string, and at some point I'm processing B's and I run out of zeros and I see that dollar sign. So I'll know that I should reject that. And that's why my B dollar sign is reject. It's a matter of walking through, convincing yourself that you've walked through all the cases where a string can be rejected and then accounting for it. And I'm not going to claim that that's easy. In this case, it's fairly straightforward. There's only a few ways this can be screwed up, right? One is there's more A's than B's. One is there's more B's than A's. And the other is once I start seeing B's, an A shows up. Those are the only three ways that a string can be out of L1. That's why down here, if I'm ever in state 1 and I see an A, notice for an A, all 3 of these are reject. Because once I'm in state 1, I should never see an A again. Now, how do you know that you found them all? You don't always, right? That's the hard part. Did that answer the question?
I think so, but I'm guessing if I
Well,
have more questions, I'll run into it on the homework.
Exactly. So you know how you get good at this is you do 80 or 90 or 1,000, right? Over and over. Like with anything else. Let's look at the next example. Now this is actually AAB star. That's actually a regular expression. And that means we should be able to create a finite state machine for it. And you did in your previous practice problems. But we can also create a push down a PDA for it. Again, if the PDA is more powerful than the finite state machine, it should be able to do what the finite state machine does and more, right? So it should be able to do what a finite state machine does. So this is just a cheap excuse to get another example in there. And I wanted to use this one because I was reserving some other forms for discussion and for practice problems. You know, if you look on the web, there's only like 5 languages anybody ever uses for these things. Like with induction proofs, you know, there's only like 12 examples out there. Okay, so AAB star. Let's see, how would we know that the strings get accepted or rejected? You know, think through what you're going to do with the stack. Don't think about making the circles and the transitions yet. Just think about what the stack's going to look like. Well, let's see, we start out, the smallest string is lambda, and we start out with an empty stack, so that's fine. We'll accept an empty string. And then the only strings that we're going to accept are of the form AAB grouped together, right? AAB, 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 right? On and on and on. Well, I can do the same trick. I just figure out what I want to do to get an empty stack at the end of a sequence of AAB. How about the first time I see an A, I push a 0 onto the stack. And the second time I see an A, I take an A 0 off the stack. Now I'm convinced myself that I've gotten a pair of A's. And now when the B comes along, I should be seeing empty stack, and I'll just let it stay empty stack. So the first A pushes a 0 on the stack. The second A removes that 0. Then the B should come along and see, ah, good, I've gotten an empty stack. And then it just keeps the stack the same. And you may be asking, well, wait a minute, Garfield. We can trick that system. AAB. I need to make these font bigger. Okay. And here's what would happen with this if we're not careful. Oh, okay, the first A puts a 0 on the stack, the second A takes a 0 off the stack, the third A would put a 0 on the stack, the fourth one would take it off the stack, and then the B comes along and it's happy as a duck because it's seen empty stack, right? So I need to figure out a way to make that not happen. And there's an easy way to make that not happen. When I see the first A, not only do I push a 0 on the stack, I go to a new state. So that when I see A 0 on the stack, I know to remove the stack, and I go to a new state. And in that new state, I'm not allowed to see any more A's. I can only see a B. So you're using now this combination of state transitions and stack content to set the boundaries for this thing. So that's why when you look here, I do, okay, Q0. The only thing I'm allowed to see at the beginning is an A, right? If my string starts out with a B, I know it should be rejected. So it starts out with an A. I'm going to go here to Q1, and the only thing I'm allowed to see now is A with a 0 on the stack, because that's what was put there when I got there. Everything else should be rejected. And I go to Q2, and I do not put anything back on the stack. So now I know that I've got a $sign on the my top of stack marker. And now the only thing I'm allowed to see is a B. If I saw another A, it would be wrong in terms of the string, because it means I saw 3 A's in a row. So the only thing I'm allowed to accept at this point, or allowed to process, I should say, is a B $, B empty stack. So B empty stack, and I'll put the empty stack symbol back up there, and now I'm ready to have another sequence of AAB. If you convince yourself that this little triangle of states with the stack manipulations will recognize AAB, well, now that you're in Q0 with empty stack, you can recognize another sequence of AAB, and another one, and another one, and another one, until the string is done. And if it ever deviates from that sequence of AAB, because of the way the state transitions are set up, you would automatically reject. It is not always trivial to convince yourself that you've found all the ways that the string can be rejected and taken them into account. If I only had one state here, and I did these A $, push $0 on the stack, A0, take one off the stack, B $, keep the $sign on the stack. If I only did those in one state, then I would accept that string that I talked about earlier, AAAAB, and the reason is first A would put a 0 on, second would take it off, third would put it on, fourth would take it off, and then the B thinks the B comes along and everything looks kosher from the machine standpoint. But you know it's not. So you have to walk through, just like with the finite state machines. Remember, you walk through and said, what's the smallest string that can be accepted? What's the next smallest string that can be accepted? And you build up all the ways the string could be accepted. And then in the finite state machine, you added into a trash state everything that couldn't be accepted. And then you hopefully exercised it a little bit and tried to convince yourself that these strings that should be rejected really didn't get fooled by your machine and get accepted by mistake. It's the same thing here, but the good thing here is all the stuff that gets rejected, you don't have to draw in. You just have the assumption that if it's not shown on the diagram, it's reject. The bad news is, because now your manipulations depend on a combination of state and stack, it may be easier to trick yourself where you might accept strings that shouldn't be accepted or reject strings that should be accepted. This is, oh, I forgot to put the picture on this page. This is processing a string AAB, AAB. And like I said in the graphic, you start out in state 0 with the $sign. You have to process the whole string. The first symbol is the A. You're popping the $sign, go to state 1, and push in. There we go. And push in $0, so the new stack is $0. Walking through. Now I'm in state 1, $0. I process the first A, so now I'm processing the second A. I pop the 0. I go to state 2. I don't put anything back. Now I've got empty stack. At 2, empty stack processing a B. I go to state 0 and I push the $sign back. And look at this line here, the $0 sign. I'll be right with you, whoever commented. This line here with the $0 sign, AAB, that's exactly like what we started out with. So what we're going to do is keep doing that same triplet of actions over and over and over again. Yeah, I think, Casey, that's for me, it was a good format. And I don't care if you use Excel or not. I'm lazy, so I did. But yes, this is a good format. If you're showing how to trace a string, I think this is a good format because you're showing exactly what's happening with your, what are you processing? What did you get from the stack? Where are you going in terms of state? And what does the stack look like when you're done? So I find this to be a good format. And we'll have an example when we do the compiler section later in the course. There's an example of how compilers actually process strings that looks similar to this too. So I didn't mind already introducing this a similar style. Here's a string that does not get accepted, and it does not get accepted because AABA, right? That's not part of AAB star. So it gets rejected because the first three symbols look fine, right? AAB, that matches. And then we get that last symbol A is processed. Top of stack is $, so that says, okay, go to state 1, put $0 on the stack. So now the top of stack is a 0, and I'm run out of string. That's what I'm using lambda there for, is it means I ran out of string, therefore I reject. I think I didn't delete all these contents from before. Now, in terms of just what would you do with the stack? Forget for now the transitions here and drawing this diagram. What if I changed this language, A to the N, B to the N, where I just said that the number of A's had to match the number of B's, but they could be all mixed up now. So strings that are in this language, strings that are in the language are AB, AB, AABB, right? That's the same. A, 1, 2, 3, 4, 1, 2, 3. That's in the language. This is still in the language, just like it was in the original one. But the idea here is I can as long as the number of A's and B's match, it's in the language. By the way, you can't make a regular expression for that, so I won't try. It's truly context-free. Just in terms of stack operations, what would you do? How does this sound? If, let's see, what are our combinations here? We can have A with a $sign on top of stack. We can have A with a 0 on top of stack. I'm going to let the zeros correspond to the A's and let the 1s correspond to the B's. I can have an A with a 1. Then I can have a B with a $sign, B with a 0, B with a 1. So here's what I would do. You need to keep, pushing things and pulling things off the stack, right? If I see a $sign, what I probably should do is push $0 on the stack, because basically what I'm going to do is every time I see an A, I'm going to push a 0 on the stack. And as long as I have zeros on top of stack, what it means is I've seen more A's than B's. So I'm going to do like I did before. Every time I see an A, I'm going to push a 0 on the stack. Every time I see a B, I'm going to pull that 0 off. And as long as I have a 0 on top of stack, then it means I've seen more A's than B's. So if I have a 0 on the top of stack when I see an A, I'll just do another one. But what if I have a 1 on top of stack? In other words, every time I see a B, I'm going to push a 1 on, and every time I see an A, I'm going to either remove a 1, right? So what's happening now? If I'm pushing 1s on every time I see a B, and 1 is on top of stack, what that means is so far in the string, I've seen more Bs than As. So since I've seen more Bs than As, I'm going to just remove that 1. And if I have B $, that means I've got an even number of A's and B's at the moment. And since I see a B, I'll put a 1 on the stack. If I see a B1, that means I've seen more B's than A's, so I'll add another 1 to the stack. And if I see B0, that means I've currently seen more A's than B's, so I'm just going to pop in a 0 off the stack. It's a little more complicated, right? Basically, think in terms of stack operations, not so much how you're going to draw the circles and things. Think in terms of stack operations first. Okay, every time I see an A, I'm going to use my 0s to track the A's and the 1s to track the B's. And so every time I see an A, I'm going to put a 0 on the stack or remove a 1. And every time I see a B, I'm going to put a 1 on the stack or remove a 0. So if you think about how you process the string, you start out with empty stack. That first symbol is either an A or a B. Let's say it's a B. That means you're going to put a 1 on the stack. That second symbol is either an A or a B. Let's say it's an A. Well, now you want to account for the fact that the A's and, you've seen a B and you've seen an A. So rather than adding a 0 to the stack for that A, which would be confusing, remove the 1. If you think about this, A, B, A, B, right? I see an A, I add a 0. I see a B, I'll take that 0 away. And now I'm at empty stack, meaning so far the A's and B's have canceled out. I see an A, I add a 0. I see a B, I'll take it off. I see an A, I add a 0. I see an A with 0 on top of stack. That means so far I've seen more A's than B's. I'll just add another 0. So now I've got 2 0s on the stack. This B takes it off, that B takes it off. With this string, the A adds a 0. This B will take it off. Now I'm at empty stack. This B is looking at an empty stack. So what does it need to do? It needs to say, hey, there's an additional B here. So it adds a 1 to the stack, adds a 1 to the stack, adds a 1 to the stack. Now I've got 3 1s on the stack. This A takes the first one away, this one takes the second one away, this one takes the third one away, and we're back to empty stack. How do you know how to do this? Well, you take a class like this, and then you do it a few times. There's a few tricks like that kind of like with finite state machines. There were probably a few tricks that you noticed were showing up over and over again, like garbage states and things or how to loop back to make sure if you had pairs of A's, you could just keep looping back to a previous state. The same kinds of tricks show up on stack machines. This is a little tougher. By the way, I claim we only need 1 state for this, because since the A's and B's can be in any sequence, we don't need to keep track of states like we did before. Remember before, I had a state, this state transition from Q0 to Q1. The only reason I had it is because I had to have all the A's before all the B's. And if an A showed up and I was still in Q0, I'd happily accept it. So instead, once I start processing B's, I moved to a new state that said, hey, if you ever see an A again, forget it, reject the string. But now in the language that I'm talking about now, the A's and B's can be all mixed up. So it's always legal to process an A. It's always legal to process a B. It's just a matter of what are you going to do about it. And so I can do it all in 1 state. It would just have 1 state with these 6 rules. Always stay in the same state. If you process an $, add that first 0 to the stack. If you process A0, that means you have more A's than B's at the moment, then add another 0 to the stack. And if you process an A1, that means you've seen more B's than A's so far, therefore keep that one popped off the stack so that A cancels out one of the B's. And then the B's do the same thing. Are you quiet because you're amazed or confused?
Amazed.
Yeah, it's a little bit of
Amazed,
both.
amazed and confused. Yeah, both. Okay, all right. It's weird that these things work, you know. We encounter a lot of things here that are, oh my God, that really works, you know, and it seems strange. But, all right, so I haven't put up practice languages. You can use the practice languages from the previous unit actually, but I'll put up a couple more. There's not that like I said, there's not that many. You know, you can go online and find some. You may find different notational systems. Don't let that freak you out. You may find some slightly different definitions that people make because they want to stress certain things in their courses. Don't let that freak you out. But you can, you know, the best way to do these is to just play around with them. Invent a language and see if, you know, invent a context-free language and see if you can create a machine that will do it, that will accept it. And by all means, post it in the discussion section so we can talk about it. Okay. I will see you. Well, Friday's going to be office hours. Okay. So again, if you want to see any worked examples or anything like that, that'd be a great time. If you ask them in the discussion section, I can post some responses there, and then everybody gets to see them too. Let's do that. Okay. All right, guys. Thanks for being here. Thanks for all the helpful feedback the other day, too.